So we're going to revise this session about interpretability and explainability of algorithms. And more every day, we lead governed by this so-called black box model. We talked about in this very workshop, the opening. They allow us to globalize huge quantities of data and to make predictions on scales never dreamed of, right? So, but there is a problem here, is that they cannot be interpreted, they cannot be explained. And we as humans somehow, and rightly so, don't trust them, right? So we need to understand, and the industry is demanding it, as we have seen in the last session, and society as a whole is demanding this. And there is also another problem, that interpretability and explainability is not well defined. It's not the same for you as for me. It's not the same for one industry or the other. For instance, in the context of tabular data, for instance, in the context of traditional regression models, we specify interpretability as the interpretation of the coefficients of the regression, right? Like, for instance, in image pattern recognition on images, we need to know which pixels of the image are being considered to classify an image, for instance, and it's totally different in terms of explanation or interpretation. So today we have 4 speakers, different, hopefully different aspects of this interpretability. First of all, we have here Enrique Valero. And the floor is yours.
So, good afternoon, everyone. My name is Enrique Valero, and now I'm going to speak about explainable AI in the context of Bayesian network. I'm going to explain the concept of independence, explain some new properties that we have formulated to increase its efficiency, and also how we have expanded this very concept to the continuum. So first of all, we are going to start with a bit of introduction, a bit of history. Well, explainable AI is probably as old as the AI itself, but it wasn't until 2012 that it was a significant rise in explainable AI papers, mainly due to the deep learning revolution, a rise in complex and algorithm methods, and a further extension of such methods in our society. However, such complex methods also leads to the possibility of them being understood by the users, which can lead in its turn to legal, ethical, and performance problems. An example of this could be the example introduced by Jesus Serna in the roundtable. For example, the credit loan example made by AI. So explainable AI is now more necessary than ever. And also, as Iñaki pointed before, this is not a clear definition of explainable and interpretability, but I personally like this definition here by Tim Miller, his paper Insights from the Social Sciences, in which he defines interpretability as the degree to which a human can understand the cause of a decision. In this case, can understand an artificial intelligence. So some of you may be thinking, okay, yes, the solution is to go back to white box models. And I don't think that's a solution because sometimes they are not as simple as we believe. An explanation still might be desirable. So a conclusion of this preface is that we need a model based on actual mathematical and statistical theory that can work with the joint probability distribution and handle uncertainty and memory variables, which is often intractable. A good solution that comes to main mind is the use of Bayesian networks, which are probabilistic graphical models that offers a great degree of modularity, thus compacting a lot the joint probability distribution. Also, they are quite semantically comprehensible. The inference is semantically comprehensible, and the relations are quite visual, which is always a nice thing to have. I'm going to explain this example here because we will be dealing with it throughout this presentation. So, so we have these two neighbors, which are Mr. Holmes and Mr. Watson, and we know that when the alarm of the house of Mr. Holmes sounds, Watson will call Mr. Holmes. And we also know that this alarm will sound if someone enters illegally the house of Mr. Holmes. So we have the relation here between a burglary occurring and the alarm sounding. Also, we know that in London, the city of our story, there are sometimes some minor earthquakes that can also trigger the alarm. So this relation over here. And finally, we know that sometimes these earthquakes are not little, they are big, they cause casualties and problems. So some of them are reported in the news. So this final relation over here. So now we go for more formal definitions and specific context. And as we said, Bayesian networks and probabilistic graphical models are qualitatively directed assigned graph that represents conditional dependencies and independencies. Also, from a quantitative perspective, Bayesian networks help us to factorize the given probability distribution and using only conditional probability distributions of each node given its parents. So this example here, we can factorize this joint probability distribution here as a product of conditional probability distribution of each node given its parents. Well, in the case of burglary and earthquake, since they are no parents, we have the marginal distributions. And here we have some examples of conditional probability distributions for earthquake, for news given earthquake, and for alarm given burglary and earthquake. Now we all know the concept of conditional independence of set of variables, and the interesting part in Bayesian networks is that many of such independencies can be identified to the concept of d-separation. So we say that two variable sets, x1 and x2, are d-separated by x3 if in all ambiguous paths between x1 and x2, there is a node C such that C and all the descendants that do not belong to x3, and C is a converging connection. There are two arrows that comes to that node, C belongs to x3, and C is not a converging connection. Maybe it's a diverging connection or a serial one. So with all this information, we can formulate, we can explain the d-separation theorem that tells us that whenever we identify a d-separation in the graph, we have also identified a conditional independence in the data. Although the reverse not always is true. It's a simple implication. Now, to understand this a bit better, I'm going to put an example. I'm going to put out examples to make sure that you follow this work. So here we can clearly see that x1 and x2 are d-separated by x3. And so we can say, following the d-separation theory, that x1 and x2 are conditionally independent given x3. A minor observation that I want to point out here is that whenever x3 is not observed, a change in x1 is propagated to x2 through x3. Keep an eye on this observation; it will become important later. So now, until this point, we have only spoken about discrete Bayesian networks, in which there are only discrete variables, but this is not always the case. There are also continuous Bayesian networks in which all the variables are continuous. In a specific case of such networks are the linear Gaussian Bayesian networks which factorize multivariate Gaussian into a set of conditional linear Gaussian. For example, the conditional density of a variable y, given its parents of y, could be a normal in which the mean is a linear combination of its parents, and the standard deviation is not conditioned on anything. And if you want a more specific example, you can just hear this factorization of marginal densities and conditional densities. As I said, the means are linear relations. So now we are going to really talk about how we do inference in Bayesian networks very briefly. So basically, since in Bayesian networks the joint probability distribution is factorized, if we want to get the marginal probability of xi, we basically have to sum for all the value assignments for all of our x except xi, the product that represents the joint probability distributions. This is a bit complicated to explain, but I think we can see it more easily with an example. So we have this product here that represents our joint probability distribution. So if we want to know the probability of the alarm sounding, we basically have to sum this product for all possible value assignments for this model for variables. Now we go for a more specific type of inference called abduction that it goes a little bit like this. So let's say we have a certain evidence, let's call it E, and a set of explanation nodes. So we want to know which value assignment for this explanation node, which will maximize the posterior probability of the explanation node given the evidence. And here you can see the formal definition, the argument of H that maximizes the posterior probability of H over explanation nodes given the evidence. And again, here is an example. If we know that Watson has called, what is the most probable explanation for a Burberry and an earthquake occurring? So we have to iterate over all values of value assignment of B and E and see which one maximizes this posterior probability. Now we go with the concept of independence itself. And in a math query, in what I just explained, the variables implied are the explanation set and the evidence E. But sometimes we are also interested in knowing which other variables are relevant to this explanation. The relevance can be somehow defined as the capacity of a variable to affecting or modifying somehow our explanation. And the traditional definition would be that the variables that are conditionally independent from the explanation, given the evidence, are irrelevant for our explanation. So in this example here, alarm and news would be relevant because they are conditionally dependent from our explanation. However, Sherlock arrives would be irrelevant since it is conditionally independent from these two variables from the explanation set given the evidence. However, are really all conditionally dependent variables relevant in a specific context, in this specific context? Let me give you another example. If we could know all the values for this node here, for news, and for any possible value assignment for news, our explanation would remain the same. Couldn't we just say that news is not relevant, even though it's clearly conditionally dependent? And this is exactly what independence is all about. So we have maximum posteriori, an explanation, H star, and an unempty set of nodes R. So we can say that the explanation H star is not independent from the set of nodes R if for every possible value assignment from R, our maximum posteriori remains the same. This concept, I think, is very useful. It gives a bit more of robustness to the concept of variable relevance. However, there are a couple of observations that have motivated our work. The first of all is that independence have some properties that are yet to be explored. They are out there, but they have not been formulated. And the second problem is related with the continuous variables. We will address the elephant in the room, and is that this definition cannot work with continuous variables. Now we go with our proposal itself. First of all, we are going to explain some properties that we have formulated regarding mapping independence. The first property is related with subsets. If we know that our explanation H star is not independent from a set of nodes R, and Ri is a subset of R, we also know that H star is map independent from Ri. And here is a bit of a proof of this, although I'm not going to explain how to find the proof. So basically, we separate the node R into two subsets, Rj and Ri. Here, it's basically the formulation of mapping independence with just the R's separated. And then we make the R maps explicit. And this expression here means that for every possible value of Ri and Rj, H star is big, the probability of H star is bigger than the probability of H over line. H over line is basically any value assignment that is not H star. So now, if we marginalize this probability, if we sum for every Rj, we get reintroducing the R max to this expression here that proves us that H star is false mapping dependent from the subset of Ri. Here is again a bit of an example. First, we perform if we have an evidence B, we perform a map query over C, and we get that the most probable explanation for the evidence B is that C is true. This is what C lowercase means. Now we study the map independence of the explanation C equals 2 from A and B. And we can see that basically for every possible value assignment from A and B, C equals 2, it's always the one that has the maximum probability. And then no matter the marginal probabilities of A and B, we know that the explanation C equals 2 is map independent from also A and B individually. Now we go to the second, last property, I promise, which is related with the conditional independence. If our explanation nodes H are conditionally independent from Rj given Ri, and we know that our explanation H star is map independent from Ri, then we also know that H star is map independent from Rj. And how, here's the proof again. So basically, now we are going to work with the conditional probabilities, the joint ones, since they are proportional. We can absolutely do this. Again, we make the R max explicit, and now we are going to multiply and solve for the probability distribution over Ri, probability of Ri. And we get that not only for any value of Ri, H star does not change, but for any probability distribution over Ri, H is not going to change. Any probability distribution over Ri cannot alter H star. And if we know that Rj can only affect H to Ri, since they are conditionally independent given Ri, Rj cannot alter H star. Again, a bit of an example to more easily understand this. So first we perform a map query. We have an evidence, any over j, and the map query gives that the most normal explanation for I is I lowercase star. Then we study the map independence of B from I star, and we see that in fact I star is map independent from B. If we know this, we also know that I star is map independent from all these nodes, because a change in any of these nodes will be propagated to I through B. And we know that any probability distribution over B cannot alter I star, our explanation. Now let's move on from the properties and talk about the continuous case. So there are mainly two problems with this definition in continuous networks. The first one is that what we are doing here with this equal operation, basically we are comparing, in case we have a continuous distribution, we are comparing two modes, which are two real numbers, or maybe a vectorial mode. We are comparing a set of real numbers, which usually the comparison will be of false because there are decimals, a slight change will give false most of the time. So the simplest solution, I think, is to basically introduce a threshold of tolerance, epsilon, and compare the difference between the modes with vectorial mode. Another option would be to eliminate this middleman, that is the mode, and compare directly the continuous probability distributions when R is unobserved and with each observation of the nodes R. And both ideas can be captured within an abstract function that we call this distance. And if we change the formulation to account for this function list, we get this formulation here. Now for each possible value R, we have to check that the distance is lower than the certain threshold epsilon. I'm not going to just spend here a lot of time, but some example of this function could be, as I said, the sum of the difference between the modes, the sum because it might be not a single mode, but a vectorial mode. And also we could take some measures of divergence between probability distribution, for example, the Jensen sum of divergence, which is similar to the Kuhlmann library, but this time it is an actual distance, or the overlapping coefficient. The second problem with map independence in continuous cases is that this definition asks us for iterating over all possible values assignment from R. But again, if we have continuous distributions, all possible values assignment from R is infinite. So again, I think the simplest solution is to do a sampling from the probability of R and check if on average the condition holds. If we merge the two changes that we have just made, we get to the definition of what we have called the epsilon map independence. Basically, is the distance between this probability when R is unobserved and probability with R lower than a certain epsilon, where R is sampled from the probability of R. Again, this relies heavily on sampling, but in some cases, maybe we can do this sampling a bit more intelligently. And this is the case of Gaussian linear Bayesian networks. And why is this? Because we can take advantage of the linear relation of the modes of each one of the nodes of the Bayesian networks. So first of all, a couple of prior observations. If we are observing a certain node, let's call it H, when R is not observed, we have these probability distributions. And when we observe R, and R is basically this mode, we can see that the standard deviation is reduced, but the mode remains the same. When we do another observation over R that is not the mode, again, the reduction in the standard deviation is the same, but this time the distribution of the mode is displaced. So with this information, we can conclude that when the distance between these two probability distributions is minimum, when the R observed is the mode of the probability distribution over R. Now we go with the, I think the eye-opening example. Again, we are performing here a map query. We have the element x1 equals 1, and here we have the marginal distribution of x2 and x3. If we want to check if x3 is independent, is map independent from x2, we will do basically a sample over x2 and see if on average the distribution of things in x3 are divergent. So let's do that. It's going to check with x2 equals 2. This yields this probability distribution here in the red. Now, if we consider these two probability distributions to be similar with our this function, we also know that for any value of x2 between its mode, which is 1, and 2, the map independence criterion is also going to be met. And we also know that in case we consider these two distributions to be dissimilar, any other check that is farther from the mean than 2, maybe 2.5, 3, 3.5, it's also not going to meet the map independence criterion. So for example, here we have, we check also 3.5, and we check that its probability distribution is more dissimilar from the blue one than the red one, which is when x2 equals 2. So what we know here is that with a single sample, our prime, we can gain a lot of information. As I said before, when our prime meets the epsilon map independence criterion, any sampling range, the mode on our prime, will also meet it. And otherwise, not all values in this range will meet the epsilon map independence criterion. So the question remains, how many and which are primes to select? We have not a clear answer for this question. We like to do some experiments with some statistical framework, but we think that a good value would be to select two R primes, which could be 2 sigma and minus 2 sigma. And why is this? Because if 2 sigma, minus 2 sigma, sorry, and 2 sigma follows the epsilon map independence criterion, any value between minus 2 epsilon and 2 epsilon will also follow the criterion. And we know that between these two values, the 95% of the probability is concentrated. So we are evaluating a big chunk of the probability with just two samples. Now I'm going to finish. I'm going to draw some conclusions because we believe that the interest of map independence is twofold. First, it will let us study from a more robust perspective the concept of relevance in node. And also the methodology is extremely easy to understand, and which is actually an explainable principle and is very useful in legislation. I know that this proposal maybe relies too much on heuristics, but still simulation methods are offering us a new field for map independence, which is the continuous state, which is very, very broad. And also 3 future ways that I see this work, other than just continuing and making some more robust experiments. First of all, extend the methodology to hybrid Bayesian networks, because nowadays most of the data set contains both discrete and continuous derivatives. And the second future way that we can see is that with the properties that we have formulated for map independence, we can design a more efficient algorithm. Again, we don't have the algorithm, but the evidence points out toward that we have to begin evaluating the map independence of H from its Markov blanket, from its closed nodes, and start from a reduced number of variables. And then we also notice that the definition of mapping dependence is actually quite related with counterfactual. Because what we are doing in mapping dependence is checking if a change in R produces a change, a counterfactual, in H. So the relation is here, and maybe slightly modifying the original definition of mapping dependence, we can somehow find counterfactuals more easily in Bayesian networks. So this is the end. Thank you for your attention. Thank you very much.
We have time maybe for one question.
Can you go to slide number 26, please?
Yeah. Okay, here.
Yeah, when you use the distance between we assume the continuous case here, aren't we?
Exactly.
So the P's are actually density functions.
Exactly.
So one problem of measuring the distance here is that it may happen that there's a big difference in density value. But if you consider just a small ball around, a small interval around the value where you measure, maybe the difference in probability is not so important. So that's something that can be taken into account. I say that because we faced a similar problem. I mean, this problem of measuring the mode of or evaluating the density at one point, the map configuration using continuous variable. For instance, if you try to decide whether a bank customer is going to be to stop paying her mortgage in 2 years or something like that, or slowing her loan in 2 years. So you try to find the configuration that maximizes that probability in order to get both kind of customers. You should somehow help to improve their profile. But then it has to do with the explainability, because maybe the answer that you get here is just one point that in fact any configuration of continuous variable has probability 0. Then it has to do with explainability, because maybe you would be rejecting a loan or something like that just because you found a maximum one peak in the density when you find. So what we did was to consider this, let's say, okay, we're going to consider map configurations that they at least have a probability 0.01. Then you define, somehow you consider the density and you start to cut from above until you cover 0.01 probability. And in this way, maybe you can avoid this kind of effects.
Yeah, in fact, maybe this part is underdeveloped, the external mapping dependence in general, because it was supposed to be a kind of preamble to the interesting part, which was the case with Gaussian linear Bayesian networks. In fact, I know that there are other problems that, for example, this thing with the distance may not work when we have a multimodal distributions. We have many modes for a same distribution. But yeah, the idea was to propose here a very, very general framework in which we can make it particular for the case of Gaussian linear Bayesian networks, Bayesian networks. Okay.